Okay, part two of the polymers section. What this section looks at a bit more is about some of the chemical properties and the physical properties that polymers have, and relating that back to the chemistry of it. So the first thing that is really important is that when we talk about polymers, they really make a long chain, okay? And that those links in that long chain are all covalent bonds. So it's very strong. It's very hard to break an actual chain itself apart, but we might have multiple chains. In fact, we will have multiple chains, and the properties of that polymer really depend on how does one chain interact with another chain. Okay, what are those intermolecular forces? Okay, that are occurring. So your dispersion forces, your dipole-dipole, hydrogen bonding, etc. So if we consider the addition polymers in particular, how it doesn't necessarily mean that addition polymers are always going to be this, but if we look at the example that's given, a very simple addition polymer in the diagram down here, then we can see that realistically there's no polar sites on it. So we have a really long chain that has no polar sites. But what we do have, because it's a really long chain, is that we have this sort of areas that have a big cloud of electrons, if you like. That's often how it's explained, because there's lots of these outer electrons from all of these atoms in this sort of long chain that's sitting there. So we do get the dispersion forces, where as the chain bends and moves and changes shape slightly, we get these temporary poles, so we get dispersion forces. And so there's going to be dispersion forces between the two chains, more than two chains, but this diagram has two chains in it, between these electron clouds. Okay, they're going to be attracted. And, the stronger that attraction, the change in the properties of this polymer. So we know that dispersion forces are the weakest of those intermolecular forces. They're easier to break, okay, and they're not permanent. They're temporary. They move. They change all the time. So that adds to the properties of this polymer. Okay, so we've got three properties written down here. So we have a low melting point, all right, because it's very easy to break those dispersion forces, so it melts. We've got to think, though, when it melts, it means that the chains themselves are still intact, okay, unless we're applying really strong heat to break those covalent bonds, but the chains themselves are free to move from one chain, like from one space to another. They're not attached to the chain next to them, okay? So low melting point. The second property, inelastic, that's really important because it actually seems a bit counterintuitive as we go through these. Inelastic, or when we're talking about being elastic, we need to think about it as being how likely is it to try and get back to the exact shape it was before. So if we think about a rubber band being elastic, we stretch it and then it comes back and snaps back to the shape that it was before. So it's quite elastic. Okay, inelastic means that it's likely to, as you bend it, squish it, change it, it stays in this new squished state. It doesn't come back to how it was. And that makes sense with dispersion forces, because as you squish it, then the changes in the shape and that the electrons aren't necessarily attracted to any other particular electrons, or electrons aren't attracted to electrons, but in those clouds aren't sort of fixed in their attraction. It doesn't matter, they'll all go and attract somewhere else. So it'll stay where it's been squished to. So quite inelastic. Makes them flexible. They can change their shape. Okay, so if it's only dispersion forces that are holding it, they're the properties you generally get: low melting point, inelastic, flexible. The sort of second type of interactions that we can get are the dipole-dipole or hydrogen bonding ones. So this first diagram, we can see the sort of interactions happening here. They aren't hydrogen bonds. Okay, there's no hydrogen involved in it, but we can see that the carbon to oxygen double bond there, that is a polar bond. Okay, and so it can cause an interaction with this one as well, and we can sort of get the chains lining up and causing this interaction, secondary interaction, so dipole-dipole. Okay, stronger than dispersion forces, and then we can also have ones that might have sites where hydrogen bonding can occur between chains. Okay, so Kevlar, hopefully you've heard of that. That's like your bulletproof, they make the bulletproof vests out of Kevlar. It's quite strong then, obviously. I'm not sure what the other one is, whether that's something that's being used, doesn't really matter. But what we see with the properties of these things as they change, we increase the melting point. Okay, they're held together more strongly, and so it's going to take more temperature to disrupt those secondary bonds. They have increased elasticity, and the part that makes it hard for us to consider there is that some of these things are harder, and we don't really consider, in our brain, we don't consider something that's hard and sort of perhaps inflexible as being elastic. All right, but in fact, it has an increased elasticity. If we can sort of squish it out of shape a little bit, and it might not squish very far, it really wants to resist that and go back to the shape it was in before. Okay, in comparison to something that has just dispersion forces. And this will obviously, well, maybe not obviously, but hopefully you can see that is going to try, once it's made these secondary interactions, they're a bit stronger. They want to stay as it is. It wants to stay in that sort of same configuration, same shape as it's in. So that's an increased rigidity. It's more rigid. It's more sort of stuck in that shape. Okay, the last one, there are some that actually allow for the bonds that occur between chains to be covalent bonds. Okay, it can actually be something that can occur. We don't need to go into the chemistry behind that as such, but perhaps you could imagine that in a sense this is a little bit like an addition reaction that might occur across there. There might have been a double bonded carbon in that space, and it can occur. So we're talking actually covalent bonds holding chains together in this case. Much stronger, really strong, hard to break. Okay, so once it's formed, you can imagine to break that down is going to be very difficult. Okay, and so bakelite is one of those hard plastics. It's most dice that you play dice games with. That's the sort of material that's what bakelite is. It's a plastic. It's a hard, really solid plastic. Very durable. It's used for lots of other things as well, but most people can sort of imagine what a dice is like. So these things, mostly their melting points increase, but realistically most of them don't melt under normal conditions. Okay, so it stays as a solid, or it will burn more than melt as such. They have increased elasticity, and that's the part that's a bit hard for us to cope with, because we don't imagine have a set of dice. You don't really imagine them as being elastic, but the idea is that yes, if you can squeeze them hard enough to deform their shape, they really want to resist that and go back to their normal, their original shape that they've been set into, and they increase their rigidity even further. They're even more solid and that sort of thing. So the chemical properties, the physical properties, are defined by how the polymer chains are connected. Dispersion forces, the dipole-dipole and hydrogen bonding, and then even up to covalent bonding between changes the properties of that polymer. The other part that it's the other dot point, which is up here, that says compare the effects of heating on thermoplastic and thermoset polymers. So there are different polymers that are what we call a thermoplastic. Okay, they can be sort of melted and reshaped, and then sort of solidify back, and they hold that shape again. So in tech, you might have used acrylic. I don't know whether you've used it, but got someone melt, like you put it in and melt it, and you can bend it into different shapes, and then it will set and stay back in that shape. So that's a thermoplastic. For them to be able to do that, they must have had the weaker secondary interactions between them. Okay, they're not going to be held together by covalent bonds. Okay, and so you can see here it talks about they have the weaker dispersion forces, and some of them that have the hydrogen bonds or dipole-dipole interactions. Okay, so lower melting point can reshape them. It does allow them to be reshaped and recycled more easily. The other type, the thermoset, have really high melting points. So they don't change their shape when they heat. They char and burn, and they don't ever really get into that molten state. Okay, so you can see most thermosetting polymers combust before they melt. Okay, they also, it would go sort of following that they must have covalent bonds as their cross links, as their forces. Okay. Notice, and this will be an interesting one because we've referred back to that. They talk about intermolecular there and intramolecular. The reason that they really call these covalent ones as intramolecular forces is the reality is if you've started to put some covalent bonds across those chains, then the multiple of those chains becomes this even bigger molecule. So it's really sort of its own one molecule. So it's internal to that molecule. The last sort of couple of bits about this are stuff that it should realistically be quite general knowledge stuff you've talked about before. So the what's the problem with these polymers? What's advantages and what's disadvantages of them? We can make them from fossil resources, so we can make a lot of our synthetic ones from your petroleum products. They have advantages, but we also are aware of those disadvantages. But we can also make them from renewable materials as well. Okay, so your polyesters and your polyamides, those condensation reaction ones, they can be made from more renewable sources. Okay, so there's a couple of tables in there that for the non-renewables, we actually do talk about advantages as well. Often, your non-renewable resources always get a bad rap, and there's reasons for that. But there are reasons we use them, and that's an advantage. Currently, we can still say that fossil fuels are abundant. We won't be able to say that forever, but currently they are abundant. And we've already got manufacturing facilities that process that sort of stuff, and we recycle those things. They're already there. So there's advantages of that sort of stuff. The disadvantages is that they're non-renewable, and they might be relatively abundant now. They're not going to be forever, and it's going to cost more and more and more. So the price of those polymers, which are relatively cheap, we can. It wasn't that long ago that shops were quite happy to just give away plastic bags because they were so expensive. So cheap. But that will change now. Obviously, the price of the plastic bags is not to cover the cost of the plastic bag realistically at the moment. It's more to try and deter people from using them. What we have as a disadvantage is that even though plastics from synthetic polymers can be recycled, most of it still isn't. And the problem with that is that a lot of it is just not economically viable to be recycled. It's not that it can't be, it's just that it's a cost. And so there are things that are happening, the red cycle and stuff like that, soft plastics which hadn't been put in there, but it is a cost, and that's a reason why it's not done as much. But most of it can actually be recycled. And if we talk about the stuff that's made from renewable resources, then the advantages are that they can be more biodegradable, they'll break down, okay? The raw materials that we can use, so things like your plants and wood and corn and potatoes and wheat and lots of things are made from starches. You'll probably be aware of the little packing styrofoamy stuff now. It used to be styrofoam. Now it's that made of starch stuff that if you put it in water, it will just dissolve. So those raw materials ultimately are relatively inexpensive. You can make them from recycled material, so dead plants, waste wood, things that were going to be wasted anyway. When it decomposes, those polyesters, polyamides, its hydrolysis it doesn't produce the toxic byproducts that other things might. Okay, and generally can be processed using the machinery we've already got. So that's good. That's a cost saving thing. There are advantages of it. The disadvantages is if we start using our crops for growing feedstock for polymers, then that's less food that's available. If we, it could change the price of those raw materials. Suddenly the food prices will go up. Okay. We have the problems with, if we're growing more crops, we're using more fertilizers, pesticides, and most of them come from fossil fuels. So potentially that's a problem that we would have to overcome anyway. The hydrolysis occurs under the right conditions, so you need to have the right conditions for that to occur. There are some disadvantages probably that hasn't been said there. Some of the biodegradable plastics, well, the problem is the bag breaks down. Now, that's a good thing in some ways. Other times, depending on what you want to use the bag for, not so great. And it costs more. Okay, so the price is a challenge with it as well. So there are advantages and disadvantages. You need to be aware of some of them. You're more likely to be asked the question, discuss an advantage, or give an advantage, or two advantages, or disadvantages, that sort of thing. Okay. So to go a little bit further with the biodegradable stuff, it asks you to say, why are some polymers biodegradable but others aren't? And what are the advantages of polymers being biodegradable? Okay, so the advantages, reducing landfill, obvious. Okay, we've already talked about raw materials to produce them are abundant, and they decompose over a much shorter period of time. The disadvantages are that a limited number of the synthetic polymers are biodegradable. So the problem is that most of our synthetic ones that we make won't break down anyway. The ones that are biodegradable, a lot of them will actually release carbon dioxide, water and methane when they break down. Okay, so when we talk about biodegradable, often they are degraded by bacteria, enzymes and things like that, and that will release some of those greenhouse gases. And for it to work, you need to have oxygen and water present, and that's a problem because if you put it into landfill and you bury it, often there is very little oxygen and very little water available, and so they won't decompose anyway. So there's that sort of idea, well, it decomposes, we can chuck it in the bin. If it gets buried very quickly and buried in that sort of environment, then perhaps it won't decompose very well anyway. So that's something that probably isn't considered a lot. And then obviously, for non-biodegradable things, then what can we do to get rid of it? How do we deal with it once we're finished with it, once it's no good anymore? Well, we can recycle it, that's okay. And look, we said before, most things can be recycled. The cost is the problem. Incinerate it and burn it. Unfortunately, still a lot of that is burnt, but we know that it needs a higher temperature, but it also produces a whole lot of gases, things we don't want. And a lot of it just goes to landfill. Okay, and it doesn't break down, it just contaminates the land. Okay, and needs to be then isolated from that surrounding environment, water sources and all those sorts of things. So a lot of those last bits are just sort of the general knowledge that we already know about, plastics and that sort of stuff. Okay, hopefully that'll help with some of the questions. Please keep firing questions into Teams if you've got any. I will probably add another video. We'll see how we go for tomorrow.